Okay, so today we consider neutrino when I say neutrino, I mean neutrino and antineutrino quark scattering in electroweak model, and then we will combine this result with quark parton model to obtain the scattering cross section of neutrino with a isoscalar nucleus and antineutrino with an isoscalar nucleus. So the two processes we will consider are a mu in its charge current reaction has to produce a mu minus. So by charge conservation, mu can only interact with a d quark. And similarly, mu bar in its charge current interaction can only produce a mu plus, not mu plus. Which means it can interact only with a u quark. And we can draw the following Feynman diagrams. Mu going like this with momentum P1 and producing a mu minus with momentum P3 and a down quark with momentum P2 producing an up quark with momentum P4. And in some sense, we can get this by looking at it sort of backwards. But anyway, let me formally draw the Feynman diagram. So, strictly speaking, we have u with momentum P2 going to d with momentum P4. And here these are antiparticles. So for antiparticles, we put the arrows in the reverse direction. So this is with momentum. And we put the momentum with a negative sign. What this means is there is a mu with momentum P1 coming like this. That is what this means. Now, let me also draw the okay, for the moment, let us leave it like that. And so we'll call this, then it's okay. reaction, I write the matrix element using the standard Feynman rules. So first I write the upper vertex, which is Ig by 2 root 2 psi bar. Okay, I'm writing it in terms of the matrix element, so I write in terms of spinors. That's a outgoing particle, so the corresponding spinor is a U bar spinor, and let me not use P1, P2, P3, P4, just to keep the, so we'll write it P mu, PD, PE, and similarly this P mu, okay. So for an outgoing particle, we have a U bar spinor whose momentum is P mu, gamma alpha. The coupling of W, this is W, and the coupling of W is a V minus A. So that's why we write 1 minus gamma phi. And that is a incoming particle. So I have and similarly this is an outgoing particle, this is an incoming particle. So the, there is the W propagator, so that is minus G alpha beta by Q square minus W square. And here it will look exactly similar. U bar PU gamma beta minus gamma U. So this is, I'll ignore factors of I. Actually, I should have an I here also. I get this to be G squared by 8mW square times, and in writing this, of course, I am assuming Q square is much smaller than mW square. I'll just write it J alpha lepton times J alpha quark. This is the leptonic part and this is the quark part. Now I do sum over strings mod mfi square. By the way, this G square by 8mW square is GF by root 2. So I write it as GF square by 2 times that the leptonic current times its complex conjugate. So I write it, if you write it out, you find that it turns out to be the complex conjugate of this, if you work it out, it turns out to be this. But I have put beta here rather than alpha because of the G alpha beta, this current, the quark current and leptonic current are getting dotted. So I have to keep in mind if I put alpha here, it means the leptonic current is dotted with leptonic current. That's not correct. So when I take the square of this, I should consider a different Lorentz index. And this times its complex conjugate will look exactly like this. Okay, this sum over spins I will put later. So U bar P U gamma alpha 1 minus gamma 5 B U bar PB gamma minus 5. Now this is the standard thing we do. So this is a row spinner, which means the rest of it is a column spinner. And what we do is we put this row spinner here and take the trace. You understand what? This is a very standard technique you've learnt in your particle physics course. What we are doing is taking a product of a row vector with a column vector. Instead of which, we are saying we'll take a product of column vector with a row vector. I get a matrix and I take the trace of it. That is same as this. So when I do that and do the spin sums, get G squared by 2 trace gamma alpha 1 minus gamma 5 U bar. When I sum over the spins, I get P nu slash plus M nu by 2M nu. This 2M nu is there purely for normalization. It will cancel out in the final formula for the cross section. So I have taken then gamma beta times 1 minus gamma 5 P mu slash plus M mu by times trace of gamma alpha 1 minus gamma 5 PB slash plus MD by 2MD gamma beta. Now this 1 minus gamma 5, I take it through P nu slash, it becomes 1 plus gamma 5. I take it through gamma beta, it becomes 1 minus gamma 5 again. I multiply it with this other 1 minus gamma 5, it becomes 2 times 1 minus gamma 5. Whereas when I take it through M nu, this 1 minus gamma 5 is going through only gamma beta. So I have a product of 1 plus gamma 5 times 1 minus gamma 5, which is 0. So And that is true in taking things through mu also. So this mu and mu, they become irrelevant because of that chiral structure in this current. It is just straightforward algebra, and if you work it out, you find that only the p mu slash terms will survive and mu and mu terms will drop out. So this is g squared by 2 times 2 into 2, 1 2 coming from here and the other 2 coming from here, trace of gamma alpha p mu slash gamma beta p mu slash 1 plus gamma phi. I am writing it as 1 plus gamma phi because here it is 1 minus gamma phi. I have taken it through p mu slash also. Therefore, it becomes 1 plus gamma phi. By the way, divided by this, all the fermion masses are here. That is just for normalization. We will not worry about it too much. And same thing is reproduced here. So I have gamma alpha pd slash gamma beta pu slash 1 plus gamma phi. Now I can apply I look up in book and write down the trace formula. So this is 2gf square by these normalization constants, and there is a factor of 4 I get from this one, and another factor of 4 I get from this one, times p mu alpha p mu beta plus p mu beta p mu alpha minus g alpha beta p mu dot p mu. That is for the 1, and for gamma phi I will have plus I epsilon alpha gamma beta, or rather I will use some other symbols, alpha rho beta sigma p mu rho. Oh, my rho should look like rho, it should not look like p. P mu sigma. Multiplied by the corresponding quark terms, pd alpha pu beta plus pd beta pu alpha minus g alpha beta times pd dot pu plus I epsilon alpha. I should put rho prime here. The reason is eventually I am going to multiply this with this. So when I use these index notation, I have to be very careful, because index notation assumes that a repeated index is automatically summed over, and also an index can appear either once or twice, never more than that. So if I put rho here, suppose I say I didn't know about this term and I put rho here and write PD rho PU sigma, then when I multiply this term with this term, I have trouble because that product will have rho occurring 4 times and sigma occurring 4 times. And by the rules of index notation, such a term has no sense. So to avoid that pitfall, I will put a prime here. Now, this is a symmetric in alpha beta, this is anti-symmetric in alpha beta. This is symmetric in alpha beta, this is anti-symmetric in alpha beta. So, the product of the two symmetric terms gives me something non-zero. Product of two anti-symmetric terms gives me something non-zero. But the product of symmetric and anti-symmetric, that gives me 0. So, we find that product of symmetric tensors gives us 2 P mu dot PD P mu dot PU plus P mu dot PU and P mu dot PD. There are 3 terms here, there are 3 terms here, so it looks as if there should be 9 terms. But when you write out the 9 terms, you find that what survives is product of these two with product of these two. That is what survives, and that is what these terms are. And product of this with this and product of this with this together will cancel product of this with this. So you will eventually get only these 4 terms. 2 is. Whereas the product of anti-symmetric tensors and in fact just before coming to class I spent some half an hour worrying about a minus sign. So there is a I times I that is giving a minus sign. So there is a minus sign there. But these two will match if rho and rho prime are the same. This is Levi-Civita symbol, which means alpha, rho prime, beta, sigma prime, they all have to be different. But both will be non-zero if rho is rho prime and sigma is sigma prime. That is one possibility. Other possibility is rho is sigma prime or rho prime is sigma. That's the second possibility. But there is an additional minus sign because 0, 1, 2, 3. What is this equal to? We have to use a convention. Suppose we say that epsilon with 0, 1, 2, 3 upstairs is 1, then this is minus 1 because From here, I have to lower the indices. Lowering the 0 index, I use 0, 0, that is 1. G0, 0, that is 1. But lowering the 1 index, I use G1, 1, which is minus 1. Lowering 2 index, that is minus 1. Lowering 3 index, that is minus 1. So, this product is minus 1. So, I times I is giving me 1, and when I take the product of these two Levi-Civita symbols, I get a factor minus 2 times delta rho prime rho delta sigma prime sigma minus delta rho prime sigma delta sigma prime rho times these product, these momenta, which is P mu rho, P mu sigma. Sorry, I was a bit careless with my notation. Since these are superscripts, this rho and sigma I should have written subscripts. Whereas here I have written correctly. These are subscripts, so I wrote them as superscripts. So P mu rho, P mu sigma, PD rho prime, PU sigma prime. So the product of the antisymmetric tensors minus times minus is giving me 2 times delta rho prime. So rho is same as rho prime, so I get a dot product of P nu with PD. Minus, now I interchange, so P nu with PU and P mu with PU. So you see that when I take the sum of the symmetric product of symmetric tensors and product of the antisymmetric tensors, the first two terms add and these two terms cancel. So I want to keep these figures. So I'll rub these things out. So this sum over spins of the matrix element square is 2gf square by product of these times 4 into 4 into 4. This is for mu d scattering. Now let me look at mu bar u scattering. So the electronic current, there is a incoming antiparticle, but for incoming antiparticle we write V bar spinner. So I have V bar of minus P. And this is actually an outgoing antiparticle mu plus, for which we write a V spinner. And here these are particles, an outgoing and incoming. So this is U bar PB and UPB. This is for U bar. So for mu bar U, this is V bar minus P mu V mu V bar P mu this is V bar minus P. Sorry. And this is PD U PD. So now VV bar summed over spins, this gives me minus P mu slash minus M mu. Oh, sorry, actually I'm minus will not be there. I made a mistake. Sorry. Now, when I talk of antiparticle spinner, I shouldn't put the minus sign for the momentum. Sorry, that was a mistake. So this is V bar. P mu. And this is So this will give me P mu slash minus mu, and this gives me P mu slash minus mu, and here of course I have Pu slash plus md and Pd slash Pu slash plus mu and Pd slash plus md. So I have here P mu slash and Pu slash Pd slash. Now the structure is exactly same as before. So I write down okay. Let me rub these things out so that they will not distract us. Yeah. So the sum over spins mi square is two gf square by pi f umf times 4 into 4 into 4. If you remember, what survived when I took the product is the product of the first two momenta multiplied by product of the second two momenta. This term is, there we had gamma alpha p nu slash gamma beta p nu slash for the neutrino scattering, and similarly gamma alpha pd slash dot dot dot, and so we have the p nu dot pd and p nu dot pu. So applying exactly same logic, we claim that this is p nu dot pu times p nu dot pd. This is for mu bar u scatter. And now let us look at these products in the center of mass frame.
these expressions are valid even at relatively low.
As they stand, they are valid at all energies. But now I am going to make the approximation that the masses are negligible. So here I have not explicitly neglected the masses. These expressions are valid even when the particles are non-relativistic. But now I am going to make the assumption that the particles are relativistic. So in nu d scattering, I have neutrino with 4 momentum given by that, and the d quark with 4 momentum given by that. So I'm assuming magnitude of momentum is same as energy, which means that the particle is ultra relativistic. Mu minus has 4 momentum, so I assume this angle is theta, and the scattering plane is the xz plane, or sorry, and if the scattering plane is the xz plane, then this is if the scattering plane is the xz plane, the y component of the momentum is 0. And the up quark has opposite momentum, minus e sine theta 0 e cos theta. Whereas in the case of mu bar u, so the nu bar and u is E0 minus E. Mu plus has E sine theta 0 E cos theta, and D has E minus E sine theta 0 E cos theta. So the matrix element square for mu d is some common factor times, let's calculate p nu dot pd times p nu dot pu in this figure. P nu dot pd is e square plus e square, 2e square. Similarly, p mu dot pu is e square minus e square sine square theta minus e square cos square theta, also 2e square. On the other hand, mfi square in the case of mu bar u is the same common factor times p mu dot pu. Pu is this and this is p mu. So that is E square plus E square cos theta. Times P nu dot Pd. This is P nu, this is Pd, which is also E square plus E square cos theta. So if I calculate d sigma d cos theta for mu d, there is no theta dependence, and one can sort of turn the crank and do all the calculations properly. If you do that, we know that it is proportional to gf square, and we see that it is proportional to here e power 4, but this is a cross section, or rather let me not put the e power 4 here. gf square has dimensions energy power minus 4. Cross section has dimensions centimeter square. So in energy units, it has to be e power minus 2. So when I put in all the other factors and do it, I will get this to be e square, because the only quantity in my whole process with dimensions of energy is the energy of the neutrino. I'm taking all my particles to be massless, so the only quantity is energy of the neutrino. So by dimensional argument, I can say that this cross section must go like gf square e square. And if you put in all the numerical factors, okay, let me consult the book and put in the correct numerical factor. I mean, here I am consulting Thompson's book, but this is given in most books. Yeah. and this is written as gf square by 4 pi square times p nu plus pp whole square. So that it's a Lorentz invariant quantity. Whereas 4 pi square d sigma mu bar u d cos theta is remember all other factors are same except that there is a 1 plus cos theta whole square extra. So this is gf square pp whole square by 4 pi square 1 plus cos theta whole square. Strictly speaking, of course, I should write this 2e square 1 plus cos theta whole square in Lorentz invariant form, but I'll just put. But for whatever argument I'm going to make, writing it in terms of this cos theta is more convenient, so I'll do that.
Pi square.
4 pi square. Now, sigma nu d is gf square 4 pi square times p nu plus pd whole square times 4 pi, because there is no angular impedance. Whereas sigma nu bar u is gf square by 4 pi square. Oh, by the way, here I shouldn't write pd, I should write pu, because the initial particle is u. Times, there is no phi dependence, so there is 2 pi, and then I integrate over cos theta, and when I integrate over cos theta, what do I get? Oh, no. There is 1 over pi. No, there is something I missed. There is a factor I missed. Because, no, there is a normalization factor I missed, because it's not. Yeah, there should be additional 1/4. That is what I have missed. Yeah, I understand now. I've been somewhat careless in writing this formula. This is 2e square times 2e square, so this is 4e power 4, whereas this is e power 4 plus 1 plus cos theta whole square. So there is a factor of 4 here, and instead here there is 1 plus cos theta whole square. So relative to this will have a 1/4. By 4 times, I have to do the integral. So when I expand, first I get 1, integral of 1 gives me 2 from 1. Then I get cos theta, I get 2 cos theta, and integral of 2 cos theta is cos square theta, but cos square theta gives me 0. If I do the integral, I get cos theta plus cos square theta plus cos cube theta by 3 to be evaluated from -1 to 1. This gives me 2, this gives me 0, this gives me 2 by 3. So this is gf square by 4 pi square e mu plus square times 2 pi by 4 times 2 plus 2 by 3. So this is 2 pi by 4 times 2 into 4 by 3. So this cancels and this turns out to be gf square 4 pi square p mu plus pu whole square times 4 pi times. So this is our main result, that the neutrino down quark scattering cross section is a factor of 3 larger than the anti-neutrino up quark cross section. Next step is translating it to neutrino nucleus cross section, and we assume that nucleus has equal number of protons plus neutrons, which means that equal number of up quarks plus down quarks. So as far as number counting is concerned, the probability of a neutrino interacting with a down quark, if I throw neutrinos at an isoscalar nucleus, the number of down quarks such a neutrino encounters is same as the case when I throw set of antineutrinos at the same nucleus. The number of up quark antineutrino encounters, it's the same.
This is isoscalar.
For isoscalar nuclei.
This is the definition.
Definition of an isoscalar nucleus is one for which number of protons equal to number of neutrons. And why am I talking about isoscalar nuclei? Because up to ion, most nuclei are isoscalar. Especially most detector materials. I mean, if you have a hydrocarbon which is rich in hydrogen, then you have a problem. But let's take water. You have oxygen and 2 hydrogens. Oxygen has 16 nucleons, 8 protons, 8 neutrons. And okay, there are 2 extra protons. So that you can think of as a correction. Ion, equal number of protons and neutrons. So large number of materials which are used as detector materials, they are isoscalar. So this is a valid approximation, and we take sigma mu n to be a integral of this dfx sigma mu bar d, which will be a function of x dx 0 to 1. We have been writing that PD, but that PD is x times P of nucleon. So in that sense, this cross section is a function of x. And similarly, sigma mu bar nucleon is 0 to 1 u of x sigma mu bar. And as I said, for isoscalar nucleon, this d of x and u of x are the same. And here most of the kinematics is same except for that angular dependence leading to that 1/3 factor. So if this is some sigma, this is sigma by 2. So this is one of the most important results which we need to pay attention in neutrino physics, and because of which, while doing an experiment, we would rather do an experiment with neutrinos rather than with antineutrinos, because our statistics will be smaller by 1/3. So we will go to an antineutrino source for 2 reasons. One, as in the case of electron antineutrinos, we have antineutrino sources available, neutrino sources are not available. But in the case of accelerator neutrinos, where getting a neutrino beam or antineutrino beam is just flipping a switch, we would rather do the experiment with a neutrino beam, and we will go to antineutrino beam only if there is a necessary physics reason which compels us to do so. So, and 1 minute, let's the time. Okay, have to stop soon. By the way, this factor of 1/3 we can also understand based on angular momentum. unnecessarily I rubbed it. So I have a neutrino and a d quark, and in the electroweak theory, particles are left chiral, and in the limit of zero mass, left chiral are left helicity. So the spin of neutrino is like this, and spin of the d quark is like this. So the net spin is 0. So for mu1 and u, again, I don't have to make any special effort at conservation of angular momentum. So any direction is fine. But in the case of antineutrino is right chiral, and in the massless limit it is positive helicity, so spin is in this direction, but up quark is left chiral, so spin is in this direction. So here you have Sz equal to +1, and if you take mu plus d at an angle theta, mu plus again is right chiral, so right helicity, so its spin is like that. This is left chiral, left helicity, its spin is like this. So you have a spin at an angle, s equal to 1 at an angle. So what you need to do is that you have to sort of expand this state in terms of, it's like going from rotational basis. I have one basis where I quantize the spin along z direction. I have a different basis where I quantize the spin along this theta direction. And there is an orthogonal transformation which takes me from one basis to another. There is a rotation matrix. And I work out that rotation matrix, and I find that when I so this S is equal to 1 along theta is equal to 1 plus cos theta by 2 times S is equal to 1 along z plus something times S is equal to 0, rather Sz along z plus something else times Sz equal to -1 along z. For S equal to 1, there are three basis states: S equal to 1, Sz equal to 1, Sz equal to 0, Sz equal to -1. So I take Sz equal to 1 along this theta direction, and I take projections of that along these three, and I get this coefficient to be 1 plus cos theta by 2. And by Sz conservation, only this is allowed, these two are forbidden. So I get 1 plus cos theta whole squared by 4 relative to this case. So that's how we can explain that additional angular dependence in the case of Okay, I will stop now. Actually, I have to go out now. And if you have any questions, you can send me an email. We can have either an online discussion or meet in TIF or at some later date, and we can have a discussion. Okay.